One of the most important of all of the applications of calculus is differential equations. Scientists will often use calculus more often than not to analyze some differential equation that has arisen in the process of modeling some phenomenon that they are studying. As mentioned before, we can model with differential equations. Differential equations have a wide variety of modeling applications, such as population dynamics, heat transfer, radioactive decay, financial trends. Differential equations also have lots of applications within physical sciences. Like, for example, they're used to model the motion of a spring. It follows a certain law. What's it called again? Hooke's law. This will be just a general video on differential equations. Here are some examples of differential equations. A differential equation is just an equation where the unknown is a function, and the equation involves derivatives. Remember, derivatives is the rate of change of something. So like a derivative that's written y prime of t, like, let's see, right here, y prime of t, underlined in blue. That tells you the rate of change of y with respect to t. So some real-world examples could be y of t in purple here, that could represent your position at time t. Y prime of t, underlined in blue, could represent your speed, how fast the position is changing. Or like if you had y double prime of t, that could represent your acceleration, how fast your speed is changing. Let's bring our attention to this example here. The rate of change of y plus 2t equals 5. You're trying to find what function y makes this true. Let's look at this example here. Y prime of t minus 3y of t equals 2t raised to the second power. Now the equation involves both y and its derivative, y prime. So the function itself and its own rate of change are linked together. Let's look at this example here. Y double prime minus 4y prime minus 5y equals 3x. This uses the second derivative, y double prime, meaning the acceleration shows up. This is called a second order differential equation. Y prime equals 2y times 1 minus y. This is a famous equation. It's the rate of change of y depending on y itself, and this models population growth or logistic growth. So when you hear first order differential equations, second order differential equations, third order differential equations, what does that even mean? The trend for naming such equations comes from the highest order of the derivative involved in the equation. So if you have a one apostrophe here, that means it's a first order differential equation. If you have two apostrophes here, that means that it's a second order differential equation. Even though there's still the first order derivative here, there's a second order derivative involved, which means that it's a second order differential equation. The highest order derivative takes precedence over any derivative below it. So like if there was like a third apostrophe here, which there's not, but if there was, right, that would be a third order differential equation, even if this one had two apostrophes. Let's work through a couple of differential equations. Now this says to solve the initial value problem, y prime of t plus y over 2 equals 5. This is a first order differential equation. And we have the initial value y of negative 3 equals 0. And this is an initial value problem because we're given an initial condition on the right there. So this is a first order linear differential equation in the following form. And perhaps this is not entirely transparent just due to the placement of the variable, so I'll rewrite it. So all I did was I moved that y to the side here and I put a 1 on top. It's the same exact thing. And I did this because now maybe it's a little bit more clear that p of t equals 1/2 and q of t equals 5. What's next is that we need to find the integrating factor. Now let's find our integrating factor. We need to anti-differentiate this 1/2. This e is gonna, we're just gonna leave the e alone. But we have to integrate that 1/2. So when you anti-differentiate 1/2, it's just going to become 1/2 times t, or t over 2. What we must do now is multiply the whole equation by the integration factor. We need to multiply both sides of y prime plus 1/2 times y equals 5 by Euler's number raised to the power of t over 2. Upon doing that, we're going to find that the answer is going to be 5 times Euler's number raised to the power of t over 2. The left side is now the derivative of a product. Let's proceed by integrating both sides. Okay, let's solve the integral. This is the formula we need to apply to integrate, because we can't forget that this is the same thing as this. So the result is going to be 1/2 over 1/2 e raised to the power of t over 2. Wait, what did I just do? Hold on, wait, something's messed up. Oh yeah, oh right. Sometimes in math, you just have to stare at it and then you'll realize what happened. 1 over 1/2 e raised to the power of t squared. So that equals 1 over 1 times 2 over 1 because I'm going to reciprocate the denominator of this complex fraction here out in front of the e. It's its coefficient. And this is going to become 2e raised to the power of t over 2, right? So then what's our argument? I think it goes like this. And let's bring our attention to this equation here because we have Euler's number raised to the power of t over 2 times y, and that equals 10 times Euler's number raised to the power of t over 2 plus the arbitrary constant. We want to get y by itself, so we'll divide both sides of the equation by Euler's number raised to the power of t over 2. Cancel, cancel. I'm pretty sure I could write this like this. I can bring this upstairs and it's going to become negative. So that just gets rid of it entirely over here. But then it gets multiplied to the arbitrary constant. But it gets multiplied to the arbitrary constant in such a way that makes it so that the negative, so then the exponent is negative. So then we have y equals 10 plus the arbitrary constant times Euler's number raised to the power of negative t over 2. But there's still more work to do, right? Because we have an initial condition right here. We know that y of negative 3 equals 0. So we're going to substitute this into our equation. And then let's move that 10 to the left side of the equation. So that would mean that the arbitrary constant would equal negative 10 times Euler's number raised to the power of negative 3/2. So this is our arbitrary constant. So what we'll do is we'll substitute c back into y of t. I think we can combine the exponents here. And then this is going to be our answer. Let's do another one. This question says a differential equation of the form y prime of t equals f of y is said to be autonomous. Oh yeah, I don't think I defined what autonomous means. Oh gosh, put me on the spot here. Okay. Well, autonomous differential equations, it's it's an ordinary differential equation where the independent variable does not appear explicitly. So like this would be autonomous. And then what's more is a real number c is a critical point of the autonomous ordinary differential equation if it's a zero of f. So the equilibrium point or the stationary point. A constant solution of the ordinary differential equation y of x equals c is called the equilibrium solution. There's a couple different types of equilibrium points. There's an asymptotically stable point, which is like an attractor, and then there's an unstable point, which repels, like these little like slopes. I'll show you guys. It would probably be better if I just worked through this problem. Before we move forward, I just want to reiterate really quickly, an autonomous differential equation is an ordinary differential equation where the independent variable does not appear explicitly. Where was I? Oh yeah, they give a little bit of a definition here. Okay, so a differential equation of the form y prime of t equals f of y is said to be autonomous. The function f depends only on y. The constant function y equals y sub 0 is an equilibrium solution of the equation provided that y sub 0 equals 0, because then y prime of t equals 0. The solution remains constant for all t. Note that equilibrium solutions correspond to the horizontal line segments in the direction field. Note also for autonomous equations, the direction field is independent of t. Consider the equation y prime of t equals y times y plus 3. Guys, there's a lot to unpack here. Let me start here. Line segments, so what they mean, it's like a lineal element. So let me define, like, the line segment is a lineal element that shows the slope given by values of f of x and y, but it's given at each point. So what does equilibrium even mean? An equilibrium solution is a constant function. Think y of t equals y sub 0. Now if y is constant, then its derivative is 0. Y prime of t equals 0. Let's check out our equation here. We're going to set the right side equal to 0. The differential equation says that y prime of t equals y times y plus 3. For the equilibrium, we need y times y plus 3 to equal 0. That way we can set each factor to 0 and we can solve. So what's going to happen? We're going to have y equals 0, or we have y plus 3 equals 0. What else? We have y equals 0, or y equals negative 3. Y equals 0 or y equals negative 3. So what I'm going to do now is sketch a direction field for either side of the equilibrium solutions. These are equilibrium solutions. That stands for equilibrium solutions. Now, all right, so we're going to look at this graph here. I feel like I don't need to say that this is not drawn to scale, but this is the origin here. So -1, -2, -3, -4, -5. Let's draw our equilibrium solutions. The first equilibrium solution is going to be 0, which means it's going to just sort of span across the t-axis here. This is the t-axis, right? Instead of x, we have t, and then so the horizontal axis is t. The vertical axis is still y. We drew out our first equilibrium solution at y equals 0, and then our second equilibrium solution is at y equals -3. Do you remember like back in like middle school when we used to like calculate the slopes and stuff? Here's a quick refresher on that. If the slope looks like this, it's positive. So like really quickly, let's just remember our x and y graph, right? X, y, and we're working in the first quadrant. Here's the origin. All right, and if you think about like a graph, um, let x represent time, y can represent money. Horizontal time, vertical money. Now, if you see like even if you just like think about this like if you have like a stock, right? And you see this, oh yeah, that's good. That's positive, all right? Okay, but if you see this, that's not nice. That's not good. That's negative. The money is it's depleting. Therefore, this is a negative slope. Why is this relevant? Well, we'll get into that in a minute. So our first equilibrium point, it's y equals 0. And we want to find what the directional field is going to look like in this partition, this sector here, the upper sector. So we need to start plugging in numbers to this equation here that are greater than 0. So let's plug in to our equation for numbers that are greater than 0. What's greater than 0? 1. So for y times y plus 3, we're going to plug in 1. It's going to be 1 times 1 times 3 equals 4. We're not so much worried about what the actual number is, more so that it's positive. All right, this is positive, which means that this sector here is going to be positive. Let's look at the middle partition, below 0, but not just below 0. We need a number that's between 0 and -3, right? Because -3 is our equilibrium point and 0 is our equilibrium point. What's a number between 0 and -3? Let's do -2. We're going to plug in -2 to our equation. So the answer to this is going to be -2, which is negative, which means that this partition, this sector, it's going to be negative. Finally, for the last sector, we need to find which way the slopes are going to be going. So we need to plug in a number that's less than -3. Wait, I just realized this. Hold on, wait. Not to be scatterbrained, but this is a video on mathematics. Should probably use proper mathematical notation. All right, so we need to pick a number to plug in that's less than -3. Let's pick -4. The answer to this will be 4, but +4. So this sector here is going to be positive. So these are the equilibrium points. Let me draw out the slopes, and just remember that this is a positive slope and that this is a negative slope. So just note as we move upwards in the vertical direction, the slopes they're all positive, but they start to become a lot steeper as we move away from the equilibrium point. Let's draw the slopes for the middle sector. Note how these slopes interact with the lower equilibrium point. They're drawn to it. They're repelled by the upper equilibrium point and drawn to the lower equilibrium point at y equals -3. Let's draw the final sector. Now, there's one more thing that we have to do. We need to draw the curve that corresponds to the initial condition. Say this is a given initial condition for the problem, right? Y of 0 equals -1. That means that our solution curve, it's going to start at -1. But the behavior of the solution curve, it's going to follow the directional field. It's going to follow these line segments. It's going to follow the trend of the slopes. So we'll trace it along the slopes in this middle partition here. It's going to go like this. Whee! But you see how it's going to interact with the equilibrium point asymptotically? Well, that doesn't really look asymptotic. Hold on, wait. So it's going to follow the trend. And then it will behave with the equilibrium solution asymptotically. So yeah, that's what that looks like. Let's do another one. This question says, consider the following logistic equation for t being greater than or equal to 0. Sketch the direction field And then to draw the solution curve for each initial condition, and then to also find the equilibrium solutions. Assume that t is greater than or equal to 0 and p is equal to or greater than 0. And we're working with p prime of t equaling 0.5 p minus 0.001 p squared, with the initial conditions being p of 0 equaling 10 and p of 0 equaling 40, as well as p of 0 equaling 80. That said, let me just write out the equation here. A logistic equation can be written in this formula. And then a graph of a logistic equation of this form can be written out as follows. Here, A is the equilibrium point. So that's the formula of a logistic equation, and that's what it looks like graphically. So we have this equation here, and we want to put it into this logistic equation form. So in order to put it into logistic equation form, we're going to factor out 0.001p from both terms in this equation. If we factor out 0.001p from 0.001p squared, we're going to get 1. What we need to look at is the 0.05p. So to divide these two terms, we can look at the amount of decimal places that follow the decimal point in the divisor. 1, 2, 3, and then we'll multiply 1 times 5, and that's going to be 5. But since we have 1, 2, 3, we're going to move the decimal place over to the right. 1, 2, 3. And so what we're going to have is 50p. Let's write out our critical points. Okay, so these are our critical points. Why? Because 50 minus p, and then if you move the p over to the right side of the equation, then it's going to be p equals 50. So here's our critical point here, or our equilibrium point, 50. And our other equilibrium point is 0. Now we want to find what the slopes are going to look like in this sector here above 50. In order to do this, we're going to plug in any number above 50 into this factored form of the equation that we have, our logistic equation. We need to plug in any number above 50 into this equation here. So how about we plug in 60? The answer to this equation here is going to be negative 0.6. More importantly, it's going to be negative. Now we want to find if the middle sector is going to be negative or positive. And what we need to do is we have to plug in a number, any number, between 0 and 50 into our equation here. Well, how about we plug in 40 since that's between 0 and 50? The answer to this equation here is going to be 0.4, which is positive. That means that this middle partition, this middle sector will be positive. Lastly, we want to find this partition below 0. So we need to plug in any number that's below 0 into our equation. Well, how about we plug in negative 1 since that's below 0? The answer to this here is going to be negative 0.051, which means that it's going to be negative. Okay, so we got negative, positive, and negative. What I'll do now is attempt to draw this out graphically. We already have our first equilibrium point, which is at 50, so I'll put a 50 right here. Note that the upper sector, it's going to be negative. So the slopes of the graph are going to look like this. Note how they change in orientation. That's on purpose. Oh yeah, and over here we should have an arrow pointing downwards because it's negative. And while this is positive, we'll have an arrow pointing upwards. And then while this is negative, we should also have an arrow pointing downwards. Now I can draw the positive slopes for this area here. And then I'm also going to draw the slopes for the negative sector at the bottom. I just realized something. I need to make this taller. Now what I'll do is I'll draw the solution curve for p of t equals 10. So if I'm drawing the solution curve for p of 0 equals 10, it's going to be like down here somewhere. It's going to follow these slopes. It's going to trace along it, if you will. Next, I'll draw the solution curve for p of 0 equals 40. That's going to be right here. It's going to interact with the equilibrium point asymptotically. And up here, this is why I needed to extend the graph, because we're going to draw the solution curve for p of 0 equals 80, and that's going to be like way up here. And it's going to follow these slopes and interact with the equilibrium point asymptotically. Now we're asked what the equilibrium solutions are. The equilibrium solutions were previously determined. f of p is 0 when p equals 0 down here, and when p equals 50 up here. So that's how you draw a phase portrait. Well, this one's a little bit more straightforward. It says, determine whether the following equation is separable. If so, solve the given initial value problem. Y prime of t equals 4y times Euler's number raised to the power of t, where the initial value is y of 0 equals 1. First thing that we need to do is rewrite y prime as dy over dt. So what's that going to look like? Well, it's going to look like this. Now, what we should do is put all of the y's onto one side and then all of the t's onto another side. We're going to separate the variables. Now, I want my videos to be accessible for everyone. Like, I want anybody and everyone to be able to follow this logic regardless of preliminary prerequisites. So, a lot of people know that E stands for 2.718281828, but a lot of people don't, and that can be very confusing. When I say let's separate the variables, let's put all of the variables of one family on one side and all of the variables of another family on another side. They might ask, well, what about E? Is E not a variable? No, E is not a variable. That stands for Euler's number, Leonard Euler. It's also called the exponential, but it's equal to 2.718281828, and it goes on forever, akin to pi. Maybe I should have mentioned that earlier, but better late than never, I guess. So we want t on one side of the equation, we want y on the other side of the equation. So what we'll do is we're going to divide this by y. So on the left side of the equation, we'll have 1 over y dy, and then on the right side of the equation, we'll have 4e raised to the power of t dt. Next up, we're going to integrate both sides. All right, so I'm going to simplify this further, and I'm going to factor out that 4 since it's a constant. All right, and a rule can be applied to the integral of 1 over y, integration with respect to y. And then a rule can also be applied to taking the integral of Euler's number. Don't forget that plus c. All right, let's go ahead and integrate. At this point, we want to solve for y. But how are we going to solve for y? We're going to exponentiate both sides of the equation. And then what ends up happening is that Euler's number is going to cancel with the natural logarithm. So here's what we'll have. We have the absolute value of y equals Euler's number raised to the power of 4 times Euler's number raised to the power of t plus the arbitrary constant. Let's split up the exponential. Let's split up Euler's number. Now c is going to overpower Euler's number, and this is just going to become the arbitrary constant. So that means that we're going to rewrite the solution. I guess not overpower, but it absorbs it. That's the terminology I've been using. It absorbs it for the sake of consistency. We'll say that E gets absorbed by the arbitrary constant, and thus the solution will end up looking like this, such that C is any arbitrary constant, any non-zero constant. What we'll do now is we're going to use the initial condition. Now, as we've established before, y of 0 equals 1. At this point, we can drop the absolute value. So here's the solution. Now we can apply the initial condition. Since the initial condition is y of 0 equals 1, we can rewrite the equation as follows. I think what I'm supposed to do here is divide both sides of the equation by e to the 4th power. Because in doing this, we can isolate the arbitrary constant. We can bring this e raised to the 4th up to the numerator, but the exponent will become negative. All right, so that means that we found what our arbitrary constant is equal to. And since this is our solution, we can put these two together, and we'll just substitute e to the negative 4th where c is. And then this can get simplified further because these are both the same. They both have the same base. And then we can simplify this even more if we want to factor out 4 from each term here. And this will be the solution for the initial value problem. Let's do another one. Now this question says to find the general solution of the following equation. Express the solution explicitly as a function of the independent variable. And we have dy over dx equals y times 2x squared plus 6. We are to solve this equation and write the solution explicitly as a function of x. This equation is separable because a differential equation is separable if we can write it so that all the y's are on one side and all of the x's are on the other side. So Variable 1 goes to the left, variable 2 goes to the right. And since the right side is a product of a function of y and a function of x, it's separable. So we're going to separate the variables. We're going to divide both sides and then multiply both sides by dx. Let's go ahead and start by dividing by y. And then these guys will cancel. And then we will multiply both sides by dx. And then these guys will cancel. So this is going to give us 1 over y dy. And then on the right side, 2 times x squared plus 6 dx. So on the left side, we have 1 over y dy, and then on the right side, we have 2x squared plus 6 dx. Now the variables are on separate sides of the equation. So we're going to move forward by integrating both sides of this equation. This here, we can apply the linearity rule for integration. Some people call it the sum and difference rule. Specifically, we're going to be using the sum rule. Right, this is the formula that's to be applied. This term here gets the constant multiple rule for integration. I suppose you could just let this serve as a proof that we're going to factor out that too. Okay, now we're going to hit this equation here with 3 separate rules for integration. I'm going to draw them right here. The colors will correspond to the integral that the rule is being applied to. Let's solve this integral on this left side of the equation. ln of the absolute value of y. Moving on to the first integral on the right side of the equation. That 2 is already factored out, and we're going to apply the power rule to this integral. It'll look like this. Now there's still more work to do, but we're actually going to move on to this final integral on the right side of the equation, which is just going to be 6x via the constant rule for integration. So we're going to get that 6x, and then we're going to tag a c on the end of that. This here, within the parentheses, it's going to become x raised to the third power over 3, but then we still need to multiply it by 2. Now this term here is going to become 2/3 times x to the third power. We'll grab our 6x and then plus c. Now what we want to do is solve for y. In order to banish the natural logarithm for both sides of the equation, we're going to exponentiate both sides. In other words, we want to get rid of this natural log, so we're going to exponentiate both sides. And we'll get a cancellation right here. This Euler's number cancels with the natural log. Moreover, we can drop those absolute value signs from the y. Now we're going to split the exponential. Now this c is going to absorb Euler's number, so it's just going to become c. So the general solution for this equation will be written as follows. And this will be our answer, such that c is any real constant. We have to find the solution of the following initial value problem. Y prime of t equals 8 times t times Euler's number raised to the power of t. And then the initial value is going to be y of 0 equals -6. So we want to find y of t by integrating. Since y prime of t equals 8 times t times Euler's number raised to the power of t, we can integrate both sides of the equation. Upon integrating y prime of t, we'll find that we'll have y of t. We're getting rid of that prime because the prime indicates that it's the derivative of something. And when you anti-differentiate, it's no longer the derivative anymore. You take that prime away. As for 8 times t times Euler's number raised to the power of t, that's a different story. I'm going to pay close attention to this here, and what I'm going to do is I'm just going to factor out that 8. How are we going to integrate the indefinite integral of t times Euler's number raised to the power of t integration with respect to t? In order to integrate that, we have to use integration by parts. Now here's a cool trick for integration by parts that my professor, Michael Farquhar, showed me how to do. Integration by parts has a formula. Ultraviolet, super, voodoo. Now let's just investigate what's going on here. U times dv. We use integration by parts when we're trying to take the integral of a product. In other words, we use integration by parts when you have an integral, and within the integrand, it's something multiplied to something else. But if we're going to use integration by parts, that means that we need to assign values to the variables. So we need to know not only what u is, but we need to know what du is, the derivative of u. We need to know what v is and the derivative of v, dv. But this is what we have here. These are of the same form. We have to assign u, and we have to assign dv. But how do we determine what u is, and how do we determine what dv is? That's where Liate comes in. I know it sounds like I'm just making things up, but bear with me for a second. This is Liate, and what it stands for is logarithm Inverse trigonometric function, algebraic, trigonometric, and exponential. Logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. What Liate does is it's a blueprint to telling us which terms have precedence over what we want to assign to u. As you can imagine, if we assign different things in the integrand to u, we're going to get different answers. So Liate lays out for us the precedence that different terms have over one another when it comes to assigning u. So how does that go? Logarithm. We do not see any logarithms in the integrand. Inverse trigonometric functions. We do not see any inverse trigonometric functions in the integrand. Algebraic. T is algebraic. Any variable by itself, algebraic. Therefore, we're going to assign u to be t. That means that e raised to the power of t is going to be dv, because we've already assigned u to be, and the only thing left is e raised to the power of t. We can find du by taking the derivative of t. If you take the derivative of any variable, it's always going to be 1. Therefore, du is going to be 1 dt, or just dt. Now we have dv equals e to the power of t. Since dv is the derivative of something, since e raised to the power of t is the derivative of something, which technically speaking, we should have a dt here. And there's not really much that's technical about it. There should have been a dt there. What we're going to do is we're going to integrate in order to get v. Now, when you take the integral of e raised to the power of a variable and you integrate with respect to that variable, it's just going to be e raised to the power of that variable. What does that mean for us? That means v is going to be e raised to the power of t. Right, so from here to here, we differentiated, and from here to here, we anti-differentiated, we integrated. Now we have everything that we need for our formula, ultraviolet super voodoo. So we can't forget that 8 on the outside, so we're just going to bring out that 8. And then in our parentheses is where we're going to plug in this formula, ultraviolet super voodoo. The first thing that we're going to do is we're going to plug in u. What do we have set to u? T. So the first thing that we put in our parentheses is a t. Next up comes the v. So what did we set to v? We set e raised to the power of t to v. Then we're going to subtract, and then we're going to take the integral of something. We're going to take the integral of what we set v to, which is going to be e raised to the power of t. And then we're going to plug in what we set du to, which is just going to be dt. We already have the formula for taking the antiderivative of e raised to the power of a variable. It's just going to be e to the power of that variable. So we took the integral of e raised to the power of t, and we got e raised to the power of t. And inside of these parentheses here, we have a statement that's factorable. I can factor out e raised to the power of t from both of these terms. And of course, we're going to have that plus c at the end there. So this is going to become y of t. So now we have to distribute our 8, and we're going to have y of t equals 8 times Euler's number raised to the power of t times t minus 1 plus c. We know that y of 0 is negative 6, so we're going to plug in t equals 0. And then I can simplify this further, and we'll find that c equals 2. So we found our arbitrary constant. So I'm just going to plug in c equals 2 into our general solution here. So our answer is going to be y of t equals 8 times t times Euler's number raised to the power of t minus 8 times Euler's number raised to the power of t plus 2. And there's another way that we could write this if we just factor it. This is another way that we could write our answer. We can actually check our answer. And we could do this by differentiating our answer. 8 times e raised to the power of t times t minus 1 plus 2. Why? Because the original differential equation was y prime of t equals 8 times t times Euler's number raised to the power of t. So to check our answer, we can take the derivative of y of t to see whether or not it becomes 8 times t times Euler's number raised to the power of t. So since we want to take the derivative of 8 times Euler's number raised to the power of t times t minus 1 plus 2, we need to break it into 2 parts. We're differentiating this, and it has 2 parts. And this is due to the sum rule for differentiation. So this says that if you're taking the derivative of one function plus another function, it's going to equal the derivative of the first function plus the derivative of the second function. Oh my gosh, wait, I just realized I made a mistake. Instead of having an x down here, we're actually going to have a t down here, since that's the variable we're working with. We're differentiating with respect to that variable. Now, we're actually differentiating 2 separate functions. The first function that we have to differentiate is 8 times Euler's number raised to the power of t times t minus 1, and then the second function that we need to differentiate is going to be 2. So let's start working on the first one. The first thing to do is to pull out that 8. And then we have to take the derivative of 2, which, spoiler alert, is just going to be 0 because it's a constant. Now let's address the slightly more intricate derivative. How can we handle this? In order to properly differentiate this, we need to use the product rule for differentiation, and this function contains one function inside of another function. The product rule for differentiation can be written as follows. Let f of t equal e raised to the power of t, and let g of t equal t minus 1. Now let us unveil their derivatives respectively. The derivative of e raised to the power of t is just going to be e raised to the power of t. The derivative of t minus 1, well, the derivative of t is 1, and then the derivative of negative 1 is 0, so that means that the derivative of t minus 1 is going to be 1. Alright, so e raised to the power of t times t minus 1 plus e raised to the power of t times 1 is going to simplify. So we'll move forward by factoring out e raised to the power of t. But let's investigate this parenthetical statement here. Negative 1 and positive 1 are like terms, and they're going to cancel each other, and it's just going to be 0. So we'll have t minus 0, which is just going to be t. So this is going to become e raised to the power of t times t, which can be rewritten. I'll put the variable first such that this becomes t times Euler's number raised to the power of t. So this is what we got, right? All right, so we had y prime of t equals 8 times the derivative of e raised to the power of t times t minus 1. Okay, then we found that the derivative of Euler's number raised to the power of t times t minus 1 equals t times e raised to the power of t. And then we still have to multiply back that 8, right? So we're going to have 8 times t times Euler's number raised to the power of t. Then I'm going to multiply t times Euler's number raised to the power of t by 8. And we'll find that y prime of t equals 8 times t times Euler's number raised to the power of t. That's our answer. Thank you for watching my video. Imagine I'm not recording.